CloudDB, shaping your new normal.
Hello, everyone. Welcome to this presentation. In this session, we are going to discuss how to boost database performance 21C database with persistent memory technology. Just quick introduction about myself. My name is Kai Yu. I work for Dell Technologies as a distinguished engineer. I'm responsible for Dell EMC database solution engineering. I have been in industry for over 28 years. I specialize in Oracle database and underneath the infrastructure such as the server, storage, networking, virtualization, OS, cloud. I also spend some time working on the emerging technologies such as machine learning. See, in the last 15 years, I've been a frequent speaker in the IT conference and Oracle conference. So I also joined Oracle ACE Director community in 2010. I also keep my personal Oracle blog. That is this link. You can search Google my link by using my name plus Oracle or Dell. So I've been recently published machine learning for Oracle database professionals book in A+ book. I'm the one of the co-author. So we're going to discuss a few topics. One is we're going to have a quick introduction about persistent technology. Then we're going to discuss what are the benefits that persistent memory technology can provide for database performance, such as persistent memory, memory mode, and epidirect mode. And what are the challenges to leverage this technology for Oracle database, especially the two new features that Oracle introduced called PMEM Filestore in 21C and PMEM and the Oracle memory speed file system in 19C. Both are the features that are designed to support the PMAN epidirect mode for Oracle database. Now we're going to have quick introduction about how PMAN persistent memory is used in Oracle Exadata platform. So persistent memory technology is the one that introduced by Intel. So this is the new, is a solid state high performance memory device. And this memory device looks like very similar to a memory card. And also you can plug in this memory card, this persistent memory into memory slot. So looks the same to memory card and plug into the same location, which is memory bus. This is kind of a new tier between the DRAM memory and the storage in terms of performance. This table shows the different I/O latency speed. So the fastest one is DRAM, and also you have SD, but the persistent memory is still between. So the difference is an order of magnitude in terms of the speed and also latency. So you can have 3 different size capacity to 128 gig, 256 gig, or 512 gig for each card. And the most important characteristic of this card is they can be configured as a memory as well as storage. When you configure as a memory, it is volatile, means when you server out of power, the data stored in the memory card will be lost. But if you configure as a storage mode, which is called a non-volatile storage mode, the data will be preserved, will be persistent, even you shut down the server. So, and as we just discussed, this can be coexist and plug into the memory device. So this is actually the pyramid in terms of the storage pyramid. And this line, anything above this line is memory. Anything below this line is storage. Means storage means persistent. Memory means volatile, non-persistent. And PMAN is sitting between. The line is across the PMAN. It's called the Optane is a product name. It's really PMAN, persistent memory. And the Optane itself can be have two different products. PMAN for a memory device. There's a PMAN for SSD. So you have to make a distinct difference. So the PMAN, Optane SSD is a disk. The Optane PMAN can be configured as a memory or storage. So this is an example to show how we actually use this in the server. I'm just using this Dell server as an example, very similar to other vendors. So in this server, we have so each server CPU, I mean the socket. In this socket, we have a multiple core, and in tied to this socket, we can have a total 8 memory channel, and each memory channel can have 2 slots. So totally each CPU can have a totally 8 memory channel, 16 slots. But for 2U server, like such as R750, we have a 2 socket machine. So it means we can have a totally 16 memory channel for both process. And so this is for 750 2 socket machine, we can have totally 72 slot divided by A1 to A16, B1 to B12. A1 is for basically CPU 2, and B1 is for CPU 1. And you have you actually can mix the DRAM with persistent memory on this slot. But the recommendation, there are actually 6 different the configuration in terms of how we mix it. So those are the support configuration. So we can, for example, this is the one. I can have a total 16 for DRAM, another 16 for persistent memory. So the idea is you have to put a kind of one DRAM, one PMAN, kind of yeah. So you kind of mix them together. So as we discussed the PMAN itself, there are 2 different operating mode. Can be memory mode or can be AppDirect mode. When you configure memory mode, it is just work as a memory, and the only difference is they may have a bigger capacity. It is also volatile, which means when you shut down server, the data stored in PMAN is not persistent. When you configure PMAN as a memory, the OS can see it immediately. You don't have to do anything. So the only thing you have to configure is in the BIOS. Make sure so those PMAN are configured as a memory mode. But you also can configure as AppDirect mode. In this case, PMAN will be used as a persistent storage, just like a SSD. But the only difference is unlike SSD is by the block device. But the AppDirect mode, the PMAN in AppDirect mode will be bi-addressable, means that every time when you read data, it's not by block, it's by byte. You could do the mixed, half of memory mode, half AppDirect mode, but in some, depend on server, some server not supported. So this is actually the Intel storage memory pyramid. So here's the line. Anything above that is memory. Anything below that is storage. That means storage means it's persistent, and memory means it's non-persistent. you can see that this is the persistent memory. So the same persistent memory can be on storage, used as storage, also can be used as a memory, as we discussed. The difference is the line. This one, all this blue arrow is actually called memory bus, which means all the storage device or memory device connect this is connect to a memory bus. So this is actually, so anything here underneath is a memory bus. So this is a memory bus. But other like this green color, those are plugged into PCIe bus. So there's a special PCIe bus device connect those. The difference is usually the memory bus is faster than PCIe bus, which means in general, the device connect to this green blue line is faster than this green line. So here's the configuration. So you basically come to the BIOS, tell BIOS that this will be used as a persistent app direct mode. So in this case, I configure total 16 PMAN. Each one is 256 gig. So totally is 4 terabyte. So so when you configure BIOS, then I actually can show this on OS. Those are OS command. So for example, this will show that I have a volatile memory, which is DRAM, 1 terabyte DRAM, and also I have app direct, which is volatile 1 terabyte, non-volatile 4 terabyte. So you actually can see that. That's how OS can see. And when we configure PMAN, we actually doing called a configures region, means we have to do interleave, combine the 16 or combine 8 together. So for example, I have total 16, a total 4 terabyte. I can configure 8 of them combined together, make one region, and then make region 1, and then make another 8 of them combined together to region 0. So basically, you can then call interleave, group them together. And when you group them together, you can use them together. So Intel has actually published some study to compare the PMAN with DRAM, compare persistent memory with DRAM, and also compare persistent memory with NVMe device. As we know, NVMe device is also very fast device. But we see that DRAM, persistent memory of both DRAM, they are plugged into the memory device, memory bus, so which is faster. So performance-wise, very similar. But PMAN compared to NVMe is a 12/1. So 12, which means PMAN is about 12x time faster, 3x to 12x faster than NVMe. The one of the reason is actually they are plugged into a different memory bus, either on memory bus or PCIe link. So usually PCIe link is actually slower than memory bus. So when you configure memory mode, let's see how it works. So when you configure memory mode, immediately OS will recognize this as a black box. It is memory. But underneath how it works, we have a memory controller to do this kind of a cache hit mechanism. So we configure the real memory with persistent memory as a 1 to 4. So for example, I configure 4 terabyte PMAN. Now I need actually 1 terabyte DRAM. So when you read the data from this black box or white box, maybe a quarter chance the data is actually read from DRAM. And in this case, if the data happen to be DRAM, this is cache hit, so it's faster. But another 3/4 chance the data will not be in DRAM, will be on the PMAN. So if data is not DRAM, the data will be read from PMAN. So in this case, the PMAN will be a little bit slow than the data direct read from DRAM. But overall, it's very similar. So we actually have a study to show that performance-wise, it's only very slight difference. But once you configure that, OS will see the 4 terabyte memory. Even you have totally is 5 terabyte because it's 1 to 4. But in this case, because the DRAM is used as cache, so you will see just 4 terabyte memory. And you actually don't need to do any more configuration in OS. So once you configure in the BIOS, OS will immediately see that. What are the benefits? Obviously, this PMAN actually expand the memory size from 1 DRAM, 1 terabyte to 4 terabyte. And usually the PMAN is actually less expensive than DRAM, much less expensive. So you could get a much bigger capacity with much low cost. So it will be much more expensive to make a 4 terabyte DRAM than just a 4 terabyte PMAN. So here are some use cases. As we know, once you expand your memory, you can make your SGA much bigger. As part of that, so redo buffer, the buffer cache can be much bigger. So you can do a lot of things. For example, you can cache table, you can cache index into the pool, so that those table index will not be flushed out. So essentially, you actually improve your I/O time because you're going to do all the logical I/O on those table. You don't have to do the physical I/O. So the logic I/O, as we know, is much faster than physical I/O. So this is actually one way to improve performance. And if you have enough, cache, you even can cache the entire database. So when you do forceful cache, you further improve I/O performance. So because you have such a big memory, if you only use the DRAM, your database may not be enough. Plug in. For example, if you only have a 1 terabyte DRAM, but your database is 4 terabyte, there's no way you can cache all the database into the 1 terabyte DRAM. By using the 4 terabyte PMAN, you could cache all of the 4 terabyte database in this PMAN device. Then you pretty much make sure that all the read is a logical read. So basically, you will reduce the DB file read, physical read, and so this is the AWR report. So we will significantly reduce the DB file read, this physical read, because you reduce this weight, your storage will be much less workload. So your storage I/O your real storage I/O latency will be improved because you will do less physical I/O. But you will see that some other things like lock file sync will not be improved because because those will actually still need to access your storage. So another bigger use case is to use the PMAN cache, the much bigger PMAN cache for Oracle in-memory database. As we know that when Oracle introduced this in-memory column store, essentially Oracle introduced 2 pieces of memory. One is called buffer cache, one is in-memory database. So buffer cache mainly is raw-based. It's mainly for OLTP. You have the one we just discussed, you cache your table by raw base. You mainly use the LRU algorithm, and you basically, this is basically support OLTP database. But in-memory column store is actually in-memory. You can cache the table. It's not using the LRU algorithm. You cache in, the data will stay there until you wash out. You force them to wash out. So LR is not going to be the LRU algorithm. But also the data will be stored as a column store. But one of the important characteristics is usually the in-memory database is used for the OLAP application, which means table tend to be bigger. So which means the in-memory column store usually need a much larger capacity than regular buffer cache. So if you PMAN is actually best fit because the PMAN has advantage for large, big capacity with cheaper cost than DRAM. So we naturally will leverage the PMAN for in-memory column store. So basically, we can significantly improve performance. So we have some study and show that the advantage. So we just published 6 months ago. We actually published the study to show how we use in-memory database, use PMAN to improve in-memory database. We use a TBCH kind of a test. So one use case is 1 terabyte database to compare 760 gig DRAM or 1.5 PMEMs. So test case 1 is we use much high compression. So in this case, the 1 terabyte database can be fit both into the DRAM as well as the PMAN. So we see the performance wise because they both fit in. So if we use DRAM as a baseline, the PMAN is just a little bit slower. It's about 25% slower than the pure DRAM. So, but what happens if we use less compression? If we use less compression, then this database, this is 1 terabyte database. The 750 gig DRAM cannot hold this 1 terabyte database because we use less compression, because the in-memory column store needs 760 gig GB capacity, cannot fit into 76 gig. So which means there's a big portion of data cannot be stored into the in-memory database. So when we run a query, partial data from in-memory database, partial data from disk. As a result, query time is much slower than the persistent memory, because in persistent memory, we have 1.5 terabyte PMAN, which means that the entire database can be stored into the PMAN. So query time, everything is from in-memory database. So it's a much faster query time. It's almost 4 times faster than the without the PMAN. For the study, we did another big database, 3 terabyte database, similar 1.5 TB DRAM or 3 terabyte PMAN. So this case, high compression case, both can fit in. So we have just PMAN, just a little bit slower than the pure memory, the DRAM. But when we use less compression, the same story, this database cannot fit into the DRAM. So we have a partially stored in the PMAN, and 80% data is stored in the persistent memory. 20% is outside of in-memory store. So it results in slow performance. If we further reduce the compression, and same way, it also cannot fit into it. So we have more data, 69% data in the in-memory database, another 31%. This was 20% outside of an in-memory store. This was a 31% in-memory store. You end up a more longer response time. So it's much slower. So this tells us by using in-memories, you actually can, because you have much bigger memory store, so you can actually further improve the in-memory database performance. So let's look at the other side. So as a result, we see that the memory mode actually benefit reduce the physical I/O, but cannot address the actual storage latency itself, because even you configure PMAN as memory, your data file is still stored in the original storage. The latency, all the I/O latency, still depend on the storage. So that's why we need to actually configure the App Direct Mode as a storage. In this case, we will store database file, the log file, into the PMAN. So this can significantly reduce the I/O latency, because the PMAN itself is famous for low latency. So this is actually the algorithm So when you use PMAN itself, is actually configured as a persistent storage. So, but the important thing is that they are bi-addressed media, not a block device. SD and hard disk are block device. There's called a direct access feature. That's the most important feature. When you use the direct access feature, so when you read the data from PMAN, this is going to be different from traditional storage. When you use traditional storage, when you read the data will first read into the buffer cache first. Then you read the data from buffer cache into the server process. But when you use the app direct called DAX mode, the application or database server process will read the data from PMAN directly. They bypass the buffer cache, also bypass the operating system I/O stack. So which means it can make a much faster performance. So simply we address this I/O latency problem. So previously in memory we reduced how much weight for sequential, but now we want to address the latency because the DB file sequential read and log file sync. Log file sync mainly is contributed by the log writer performance. So these are the most critical piece of the database performance bottleneck. So by using PMAN, we will further reduce this latency. And overall, by reducing this read and write latency, we can significantly improve the database performance for all the application type, all type of database or TP OLAP. So when you configure app direct mode, you can configure as a raw device or sector mode this way, but without application change. But the problem is these two modes are not could have some potential data corruption problem. So the idea is we should not when you use a PMAN app direct mode for database, the PMAN itself cannot be configured as a raw namespace or sector space because of the data corruption problem. So we still want to keep app address by address mode. But if we want to keep by address mode, you need to actually have an application change to recognize to support the direct access feature. So this feature was not ready until recently. This feature was ready for Exadata X8M support 2 years ago, but for non-Exadata platform, such as a regular x86 platform, this Oracle support for this app direct mode was not available until this two feature was released. So for 21C, Oracle released this PMAN data file store to support the PMAN for database. Two things. One is make sure it's no corruption. Second is make sure you have a high performance using the direct mapping buffer cache, which we just discussed. When you read the data, the Oracle will bypass the buffer cache, directly read the data from PMAN into the server process. Or Oracle took a partial of this feature, support feature, implement into 19C as a patch. But this configuration use different name called Oracle Memory Speak file system. But I think this is only guaranteed high performance and no corruption, but it did not include the direct mapping buffer cache. So let's look at the 21C buffer cache. So as we discussed, traditional database, when they read the data from disk and put into DRAM. But by using PMEM, so they don't they skip the copy data from data file into DRAM. That step is skipped. So you can do the server process will read the data directly from PMAN without migrating the block into the database buffer cache. So this avoid unnecessary. It also means much faster because you don't have to wait a lot of time when you have to read the data into cache, it's not just I/O time. You also have to wait the buffer cache, make sure buffer cache is available. So there's a memory lock. You have to wait for dirty buffer, free buffer slot. So this is like completely skipped. But this PMEM Filestore is mainly implemented in 21C. But only the one of the big drawback is this only supports a single node database, not rack. So here's the step to actually configure this. This is architecture. So underneath architecture, this is actually disk. So for example, here I have a 12 DRAM disk. So I actually use the build region. So combine all them together. I can build one region or two region. So this region is built Intel in the BIOS level. Then I create a namespace. In this case, is if you think about it, namespace is just like a device in the regular SSD. So when you have a regular SSD, you have SSD, you have to create a namespace. In this case, is a device. So created this device. But important thing is that this device has to be DAX device. In this case, called FXDX device. So basically, I have the name, the mode is FXDX. So this command is done in the OS level. Then once you build that, so this is kind of what you can think about. This is actually device. Then on this device, I will build a DAX file system. So this is configure this is a device, make a 2 partition, then create a DX file system on that and mount into this called mount PMAN, this mount directory. Then once I have this DX file system, then I'm coming to database to create this called PMEM Filestore. So, and once you create a PMEM Filestore, this PMEM Filestore will have a mount point. In this case, called U1 /U1 /DB/DB1 PMEM. So this is the actual mount point. So this is the mount point. Once you create that, this is the mount point that you're going to store your database. So then I can put all the data file underneath. So this is the mount point. Under this mount point, I can put a data file or online file, create directory under this mount point. So I have all the data file here and all the control file here. So you can make your make this as your database file system. So, and a very similar way to configure the 19C, the Oracle Memory File Speed, some Oracle Memory Speed File System called OMS. So similar way, the bottom 3 layers very similar. So you have this region that built on top of the multiple persistent memory card. Then you create DX device here. Then on top of that, you create a DX file system. But above this is a little bit different. So once you create a DX file system, you kind of allocate a piece of storage. In this case, called 14G piece of storage. This is actually a UBR file. But then you use this UBR file. On top of that is a file system to create a Oracle memory speed file system. So you see, this is actually the UBR file. I create this UBR file. Underneath, I use this UBR file to create a Oracle memory file system. So Oracle memory file system is actually a utility, the OMS FS utility. You use that utility, you log into this utility, you create this, you basically use this piece of file, you create the OMS file system. Then you mount this called /Oracle/OMS/FS. This is actually the database mount point. That's very similar to the Oracle Filestore mount point. So you can use this /Oracle/OMS as mount point to store data. So those are the setting. So Oracle 21C manual Oracle Linux installation manual, Oracle element manual, or Oracle 19C. You have to make sure 19C is only supported by 19C release 12. So this feature was available on release 12, 19C release 12, not available before 19C release 12. Okay, that's the configuration. I did this test. So let's see. I want to make sure that, this is we configure this. We want to make sure we want to run the test. Make sure that this PMAN is as fast as we discussed. So here I use the standard HammerDB workload. So in this HammerDB workload is TPC. They actually create kind of TPCC-like workload. So I put a lot of I use a very small key time or use key time, so that even I use a very small number of users, I can create a very heavy workload in the database. So here I put even 20 or 40 users. Still, each user is actually corresponding to about 1,000 users, because I put this think time, lead time is very, very narrow. So each user is representing about a regular 1,000 user. So if I put 20 users, that means it's about 20,000 regular users. So by pushing this high workload, I was able to measure the I/O response time. So in this case, the I/O response time, the DB file sequential I/O response time is around 30 microseconds. So if you compare previously, for almost about 5,000 microseconds, so 4.98 millisecond. That means it's 4,098 4,980 microseconds. But when I did PMAN, the I/O latency is only 30 microseconds. So you can compare how many times reduction from 5,000 to 30. Similar to a log file sync, was previously was about also several thousand. Let's see how many thousand. Previously was 11,000, and I was able to reduce into to 81 microseconds. So, and also no matter how many workload I put in, I actually run different workload. You can see all the storage, all this weight are user CPU weight. There's no user weight, user I/O weight. There's no I/O weight, no matter how much workload you put in on the system. So here's a TPM. This is a kind of phenomenal TPM. So 3 million TPM. And I also run different different number of users, push this CPU into very, very high CPU. This is very high core CPU. This is about 11. This server has a 120 core CPU. Total 56 physical core, 112 logical core. It's very high powerful CPU machine. I was push this very high CPU utilization, push so much workload, but you see that the DB sequential read time is still keep under 50 microseconds. Latency, this is a bit longer log file, because log file itself can be not just AK. So DB file is always configured as AK, but the log file depend on how much you can have a 120 AK log file. So, and you see the TPM, we can achieve significant high TPM. So this was a 19C. I did also 21C, very similar, and DB file read even latency even lower than 19C. So previous was 30 microseconds. This was 23 microseconds, 24 microseconds. This is probably partially contributed by the DB direct, the data file, data buffer, direct buffer mapping, which means that when Oracle read the data, they skip the copy from PMAN into buffer cache, direct memory mapping. Yeah. So log file very similar to 19C, and also try different workload, very similar, same way. There's no much I/O weight, and also the the log file weight. Everything is CPU. This is probably one of the best scenario. And very similar, I reached about almost more than 3 million TPM. So this is a very significant number. And if we try this similar into any other storage, you won't be able to get that high number. And we also tried different workload, and this is actually a curve. So you see that even I tried different workload, the DB file read latency still kept under 45 microseconds. And the latency is a little bit high because I think partial was because we pushed this database very hard. So yeah, and the this CPU almost reached 90%. This is actually more because I put a 140 user. In this case, if you time 140 times 1,000, that is 140,000 users. If you compare, because the way I configure each user is actually represent 1,000 user, because the think time, key time configuration. So yeah, that's a study, and so conclusion is that this the PMAN, even no matter they implement it into 90C or 21C, we have a huge performance boost on database. So I just want a quick look at how this for the implement in the Exadata. So that's something I actually want to further study. So in the Exadata platform, they actually use the PMAN in the storage server. So they use PMAN as a most active storage. So you have a 3-tier. You have a warm data, cold data, and persistent memory is a faster storage. That's why they use hot tier. So most active data, including log file, are stored in the persistent memory tier. But unlike the non-Exadata platform, the PMAN is installed in the database server. But here, the PMAN is actually stored in the storage server. They use the faster RDMA. So this link is for lock. All the database redo lock will directly push use RDMA into the PMAN store. So this is actually much faster. Though these are data link. So if you have a reader or writer, data read, physical reader or data write will come to here, but a log writer will come to this link. So Oracle claim they have a 90 microsecond I/O latency. So our test shows about a 30 microsecond, 30 to 25 microsecond. So, and another difference is because the database is the PMAN is used in the storage server. That means the storage server can be shared. So that's why in Exadata, in Oracle Exadata, it is supported to run multi-node Oracle rack configuration, which is a significant difference between the Exadata and also non-Exadata platform. In non-Exadata platform, PMAN only can be used for single node, single instance database, and the Exadata can be used multi-node, multi-database node, multi-storage node. Yeah, so that's the conclusion. We discussed the PMAN technology and how the PMAN, two-mode of PMAN can be used to leverage database performance. Of course, the two important features, Filestore in 21C, PMAN Filestore in 21C, Oracle Memory Speed File System in 90C. We also discussed PMAN in Oracle Exadata X8M. So actually, X9M also has similar technology. So yeah, that's so my name is Caillou. So if you have questions, you always can write an email to me or come to my blog. So this is my blog, or you can use Google search my name Caillou and Oracle Odell. Oh, so that's all I want to cover, and this is actually our white paper to have a detailed discussion about how we can use PMAN memory mode for in-memory database. So you have all the very detailed test result configuration, very detailed. This actually made it in our team. So if you have interest, feel free to read this. Yeah. Okay, that's my presentation. Thank you for attending my session, and thank you.
CloudDB, shaping your new normal.